Despite extraordinary reasoning capabilities, large language models operate in constant amnesia. Every new interaction begins from a blank state, with zero prior knowledge. This lack of memory imposes a rediscovery tax, the token cost of rederiving established knowledge. Whether re-explaining architectures or debugging flows, the model spends resources relearning. As projects grow, this compounds. The more past work done, the more expensive it is to resume. The standard industry solution is context stuffing, or retrieval augmented generation, often called RAG. RAG uses vector similarity search to find relevant pieces of data and inject them into the model's prompt. Treating the context window as a storage container to be filled with raw history degrades performance. Most injected tokens are irrelevant, creating a bloated prompt that forces the model to sift through noise rather than focusing on the task. Solving the memory problem requires redefining the context window as a strict attention budget. This separates a storage container from an attention budget. Storage crams in every text block. A budget uses a spotlight to illuminate distinct data. To manage this, researchers created the Attention Management Protocol, or AMP, optimizing the model's limited focus. Under AMP, every token is a scarce resource. Information only enters the context window if it demonstrates a measurable return on investment for the current task. Research into the lost in the middle effect shows that LLMs attend to information at the beginning and end of a prompt much better than the center. This position-dependent attention means that unoptimized bulk data doesn't just waste tokens, it actively confuses the model's reasoning. Building persistent memory requires a counterintuitive design philosophy. To improve how the model understands a project, the system must intentionally store and retrieve less information. Standard RAG systems typically retrieve fixed-size chunks of text, regardless of what the model actually needs to know. This uniform granularity ignores the specific requirements of the model's current generation step. AMP addresses this through two initial phases: capture and compress. The protocol intercepts massive tool outputs, like the results of a file search, and processes them before they are ever shown to the LLM. The output is an observation atom, a structured blob containing a title, facts, narrative, and tags. A 5-month case study analyzing 34,000 atoms found a compression efficiency ratio of 8.6. Every injected memory token now represents 8.5 tokens of original work. While using an agent to compress these logs carries an initial token cost, that cost is amortized. Because these observations are reused across future sessions, the system breaks even on that investment by the second session. This shifts the memory burden. No more reading raw logs, just high-level executive summaries, processed instantly by the model. AMP uses progressive disclosure, fetching detail only when requested. Layer 1 scans a cheap index for an overview. Layer 2 provides timeline context. Layer 3 fetches full code structures using ASTs. This targeted method used 14,000 tokens, compared to a standard 250,000. The result is an efficiency gain between 18 and 56 times higher than conventional reading tools during code structural exploration.
Because standard RAG has a fixed cost for reading any file, it remains expensive regardless of query size. In contrast, progressive disclosure savings increase as the model's queries become more specific. The model self-regulates its attention. It gets granular access, highly effective targeted data, no more raw data dumps. Any persistent memory system must account for scale. Over months of use, a memory corpus can grow from a handful of observations to tens of thousands. Standard RAG suffers an O of N cost explosion. As history grows, injection costs rise linearly. AMP uses a bounded injection policy, capping memory at 15% of the context window. Session costs stay perfectly stable, unaffected by the growing total of stored observations. This consistency is maintained by a dual index storage approach that combines structured metadata filtering with semantic search to keep retrieval times under a second.
By setting a fixed operational ceiling, the system effectively separates the scale of the project's history from the cost of the current session. The data from the Claude MEM study reveals a paradox in how language models actually use compressed information. The protocol successfully guides the model using records that have been compressed by 90%, meaning the vast majority of the original text has been discarded. This is Model A, literal recall. It assumes models act as parsers, needing exact factual sentences to produce a correct answer. If true, 90% compression should be devastating. Removing specific details should prevent the model from understanding the conclusion. However, in autonomous testing, this aggressive compression did not degrade the model's performance. It was still able to complete complex tasks using only the summaries. The fact that models remain effective despite extreme data loss suggests that our foundational assumptions about the context window are incorrect. This leads to Model B, the semantic priming hypothesis. LLMs don't use injected context for direct recall. Instead, a compressed observation atom acts as a semantic prime, activating the vast parametric knowledge learned during training. Evidence shows that simple recency-based injection is highly effective. Under the priming model, the context just needs to be good enough to activate the right neighborhood of ideas in the model's latent space. Temporal proximity provides that association naturally to the AI. Second, the study found that even title-only references were sufficient to guide the model's tools toward the correct parts of the codebase. This challenges the current industry trend toward million-token context windows. If the model only needs a signal to activate its existing knowledge, then chasing massive prompts may be a misallocation of resources. If the semantic priming hypothesis is correct, the goal of a memory system isn't factual completeness. It should be the removal of noise to isolate and concentrate the signal that triggers the model's internal expertise. The shift from storage to attention is a fundamental change in how we interface with AI. We are moving away from building massive data containers and toward engineering precise triggers. The path to effective AI memory is to retrieve less and attend precisely.